Okay, so thanks everybody for coming back to the second lecture of the day. It's my pleasure to introduce Virginia Aglietti, who is a research scientist at Google DeepMind. Thank you for being here, Virginia.
Thank you. Can everyone hear me? Okay, so it's great to be here today after a long time with virtual talk. Today I'm going to be talking about statistical causality for decision making. So I structured the talk in two parts, thinking that I was the first one speaking about causality. So we're going to probably go a bit quicker on the first part and then spend a bit more time on the second. So the first part of the talk is going to be on causal inference via causal Bayesian networks, so slightly different from what you've seen before. And I'm just going to bring you up to speed with what we need to know to be able to understand the second part, which is instead going to be covering causal decision making. And all the things that I'm going to be talking about in the second part are a collaboration with the people that you see here. So part of it is the causal intelligence team at Google DeepMind, and part of it is previous collaborator outside of DeepMind, in particular Javier, that you're going to be hearing talking today later. Okay, so let's get started with causal inference. I should say, please feel free to interrupt me at any time. Otherwise, I will just stop at significant points and you can ask questions. Please ask questions. Okay, so I thought about starting, because I thought I was the first one speaking about causality, about starting this talk thinking a bit about what is causal inference. So causal inference really looks at how to separate statistical dependency into causal inference and spurious correlation. So let's take, for example, a doctor that gives a drug to a patient and is more likely to give the drug to a patient that is a male, and at the same time the recovery rate of the patient is affected by both the gender and the drug that is given to the patient. So we can represent this phenomenon with the causal graph or causal Bayesian network that you see here, where every node represents a random variable, and we have, for every node, an associated distribution, which is what I'll call and explain later observational distribution. So we have P of G, which is P of gender, P of D given G, which is the P of drug given the gender, and then we have the recovery, which is P of R given D and G. So the goal of causal inference at a very, very high level is to be able to learn from data whether giving the drug actually helps recovery, has an effect on recovery. So standard ML approaches try to understand about the statistical dependency between variables. So they look at what we call observational distribution, which is P of R given D, which includes both the spurious correlation and the causal influence. So this is the total, let's say, statistical dependency between two variables. In causal inferences that we try to understand, disentangle basically causal influence and spurious correlation, and we do that by computing this, what we call this interventional distribution that has this notation that you've seen before, and I will tell you in a second what that is. And this is going to basically just measure the causal influence, so a specific part of the path that you see in the graph there. So in general, in causal inference, there are two different tasks. One is identification problem, which is the problem of trying to identify an expression for that distribution we do in terms of what we have access to. So it could be observational data, it could be partly experimental data, combination of both, the graph. And then we have the estimation problem, in which you actually try to estimate what you got from the output of the identification task. So you've seen a bit before the estimation problem, and I will focus on the identification problem with causal Bayesian network. So you can find some reference here in case you wanna read about it a bit more a bit later, but there's what is the difference between Bayesian network and causal Bayesian network? Now, Bayesian networks give you a way to visually express with nodes and edges the statistical dependence or independence between variables. So a direct link in this graph, in this Bayesian network, represents the statistical relationship between two variables. Now, the same type of visual representation can be used to express causal dependency or independency, and in this case, we speak about causal Bayesian network. So the meaning of an edge in a causal Bayesian network is different from Bayesian network because it represents the existence of a causal relationship rather than a statistical relationship. So for example, let's take the classic ice cream example in which you look at the level of ice cream sales, that is denoted by A, and then the number of crimes in a city, which is denoted by Y. And you see that there's a correlation between these two variables. And you can represent this correlation with two different Bayesian networks. You can have a variable A that has an outgoing edge into Y, or a variable Y that has an outgoing edge into A. Both two are describing the statistical dependency. However, if you want to represent the causal relationship between these two variables, you have to acknowledge the existence of an underlying variable, which is temperature, and is in white here because it's not observed, that is a common cause of these two, and therefore it induces some sort of correlation in the observational distribution. So there's a causal Bayesian network, those two are Bayesian networks. So in Bayesian networks, so in causal Bayesian network, we use a lot of tools that were developed originally for Bayesian network. So Bayesian networks are generally described by this directed acyclic graph G, that you see one example here, in which each node has an associated distribution, and the joint distribution of all nodes in the graph factorizes in terms of the distribution of every node, x, given the parents. That's a classic property of Bayesian network. Now, in causal Bayesian network, each conditional distribution that you see in this factorization assumes a specific meaning, and it's what we call the independent causal mechanism. So we say that, so while in Bayesian network we speak about directed path, so the path that are starting from a variable and have like consequent forward-facing, let's say, forward-pointing edge, in causal Bayesian network we speak about causal path. So we say that, there are two, a variable x affects a variable, has a causal effect on a variable y if there's a causal path in this causal Bayesian network, or a directed path. So we speak about x being a cause of y if x is an ancestor of y, or if y is a descendant of x. So we speak about, a relationship, ancestral relationship in this graph to identify whether there's a causal effect between two variables. So for example, in this graph here, you see that A is a parent of y, so it's a cause of y, but A is not a cause of q, because it's not an ancestor or a parent of q. Okay, so in general, if we look at the graph, at the directed acyclic graph, we can understand whether there's a statistical dependency or there's a causal influence and there's pure correlation. So on the one hand, the causal dependencies is given by the causal path, the directed path in this graph that are highlighted in red. So you see that A goes into Y directly and through D, and these two are causal paths, they are directed paths. At the same time, we also see that there's a non-causal path, or also called backdoor path, as it was explained before. So the non-directed path is the path that goes from A to Y through C. So when you measure statistical dependency, what you do is you measure the information flowing along all of these paths in the graph. This is very high level, but just to understand that in causal inference, what we try to do is to distinguish between these red edges, which are the causal one, and the path that is instead spurious, which is the black one. And how do we do it? We do it by computing this interventional distribution. So P of y and I know that generally the notation is P of y given do of A equal A is the same thing. And this is the conditional distribution of y in the graph, where what we do is we remove the path that we don't want, so the path that is spurious, or the backdoor path. And so we remove the information that goes from the flows from A to Y through the C, through the spurious path. But how do we actually compute this P of do of A, P of Y given do of A? There are two different ways. So in general, as was discussed before, you can either go in the system, intervene on the variables that you want to compute the causal effect for, and then actually get what we call interventional data. So interventional data are data that are observed from an intervened system. And these data are coming directly from the interventional distribution which you wish to estimate. If instead you cannot intervene in the system, what you can do is you can collect observational data And if you collect observational data, then you need to find a way to transform this observational data to be able to estimate this interventional distribution, which is your goal. And in this case, I'm making the assumption that there are no unobserved confounder. It's a very simple graph, and so the interventional distribution will be equal to this distribution of y, so in this intervened graph in which I've removed this spurious path. And in general, this observational distribution of a variable and interventional distributions are different. So, for example, if we were to compute the distribution of y in these two different graphs, you will see that the distribution of y observational is on the left, and so this summation over a and c, while the interventional distribution for y is given on the right, and it has a fixed value of a because a is fixed and is intervened. So these are two different, and in most of the cases you cannot use observational data. You have to be careful when using observational data and interventional data. Okay, question up to here? Yeah. So you generally make the distinction by drawing a graph. So the graph, it might be known or it might be unknown. So here I'm dealing with settings where we know the causal graph, and so we know whether there's a backdoor path or not, and we have to deconfound the data and take that into account. But you might also have settings where the graph is unknown. And if we have time, we're going to get to that. Okay, so suppose now you don't have interventional data, which is the classic setting of causal inference. How do you compute this interventional distribution? Now, with causal Bayesian vector, you generally have, you can use the rules of the calculus or the rules of the causal calculus to get a functional that expresses the interventional distribution in terms of observational distribution. So these are three rules that might allow you to compute the interventional distribution, and might because in some cases we say that the causal effects is not identifiable. So for example, if you have confounders and there's no way to actually apply this rule, then you cannot get an intervention, an expression for the interventional distribution within the observational distribution, and all you have to do is go intervene and observe what happens. So there are three rules. The first rule is a conditional independence rule, so I'm not going to talk about it. It's standard in Bayesian vector. It's just looking at whether some variables are independent in a graph, and so it's based on D-separation, if you're aware of that. There are two rules instead that really look at this idea of switching action or intervention with observational distribution and inserting or deleting interventions. So I'm going to give you here a very simplified form of these two, just to give you an intuition of what happens when you apply these rules. So in the first case, the second rule actually allows you to exchange action with observation. So it allows you to write an interventional distribution, which is P of y due of A, has a conditional observational distribution. And the rule tells you that you can do this, you can write this equivalence if y is independent on A in this graph where you have the outgoing edges from A removed. So G of underline A means that you remove the outgoing edges from A. So you see on the graph, on the left the graph, and on the right the G of A. So if y is independent on A in this graph, and likely you've seen that before, there's a collider there, there's C, and so this path is blocked. The vector path that goes from A to Y, A, B, C, and Y is blocked, so they are indeed independent. Then what you can write is this equivalence. You can get rid of the do, and then just estimate P of Y given A, and that's going to give you that you can take the expectation to compute the average, for example, causal effect. So what's the intuition behind it? Well, if you look at this graph G of A, this graph has all the links that are emerging from A removed. So if Y is independent on A in this graph, that means that all the backdoor paths are closed. So we've removed the outgoing edges from A. All are left are the backdoor paths. And if y is independent of a, that means that those vector paths are closed. So you can write these equivalents. At the same time, you might want to get rid of the do completely. So when is it possible to do that? Well, you can check again the independence of y, given the dependence of y on a, in this additional graph, which is G with overline A, which is the graph in which we remove the incoming edge into A. So you have again G and G in which we remove the incoming edge into A. And so the intuition behind this is that if y is independent on A in this graph, it means there are no causal paths from A to y. So I've left the direct path, the path that are emerging from A, and if A is independent on y in this graph, that means that all directed paths are blocked. So there's no way for A to have an effect on y, and we can get rid of the intervention. So these are quite important. So if these are not clear, please feel free to ask questions. Now, in general, using these rules of the calculus, we can come up with two criterion that allows you to write down the identification formula. So that's what we call identification formula. A formula that gives us the interventional distribution in terms of observational distribution. So these two vector criteria tells you, these two criteria, so vector and frontor, tells you that if there is a set Z in the graph that satisfies some properties, then you can write this equivalent. So it gives you a way to out-of-the-shelf compute this interventional distribution, the identification formula, without going into applying recursively the rules of the calculus, which you, by the way, would do for a general computation of the identification formula. So in the first case, it tells you that if there's a set Z that blocks all vector paths from A to Y, and there is no node in Z that is a descendant of A, then you can write that formula that you have on the top vector criteria. So you can go in the graph, look at G of underscore A, look at whether Z separates A and Y, so it makes the two independent. If this is the case, this is the identification formula. And you can do the same with the front door. So if there is a set Z that, and you can see here Z, such that that Z blocks that A blocks all the vector path from Z to Y, such that Z intercepts all the directed edges from A to I, and there is no open vector path from A to Z, so it's a bit of like three conditions. Then what you can do is you can write the identification formula as the one that you see above. Okay, so I'll stop for 2 minutes now, but I'll just give you a recap first. So what we've seen so far is that causal inference aims at discerning causal influence and spurious correlation among two variables. The one framework to reason about causal influence and causal inference are causal Bayesian network. Quantifying causal inference requires computing this interventional distribution, which captures the causal directed path in a CBN. An interventional distribution can be obtained either by direct intervention or by using the graph and the do calculus to write an identification formula. This is all you need for them to speak about causal decision making. Okay, so what is causal decision making? I'll try here to give a definition. There is no a unique one, so it's my personal view on causal decision making. So with causal decision making, we think about an agent that learns to act in an environment by accounting for the existence of causal relationship. Where causal relationship, this is a decision, are represented by a causal graph, like the one that we've seen so far. So what does acting mean? Acting means setting the value of some nodes in the graph. Learning to add means learning which nodes to set and which values to set. And you want to do that by accounting, explicitly accounting for the causal relationship. So there's been quite an interest in the last few years on causal decision-making algorithms, and I refer to all the work on causal bandits, causal Bayesian optimization, and causal reinforcement learning. So there are some, I've put some references here. There are some similarities among all of these problems and settings. So first of all, in general, all of these algorithms consider the existence of a causal graph that represents an environment. It could be, sort of like a bandit problem in which you play a casino and at a casino and you have an arm that represents an intervention and you observe your reward. It could be a graph like the one that I put here that represent the sort of like the policies that are used to prescribe statin and aspirin, so we go back to the same drugs. Or it could be the graph representing the Markov decision process of a reinforcement learning problem. We can observe the environment, so we can actually collect what we call observational data, but we can also interact with the environment, so we can collect a few interventional data points. Every time that we do something in the environment, we get a reward that could be of different form. And we aim at finding the policy or the intervention, so it depends on whether we speak about base-opt and bandits or reinforcement learning that maximize a cumulative reward or any other sort of reward. So these different algorithms differ in terms of the type of variable that they consider, and so the definition of the action space, continuous or discrete, the reward definition, and whether they are dealing with a static, for example in bandit and base-opt, or dynamic environment, for example in RL. So they all use the same type of framework. And I'm giving you here two examples that I will use in this talk. And one is in biology, one is in healthcare. So the first graph on the left, A, represents, this is a standard example, you might have seen SACS data that is using causal inference, that represents the relationship between different phosphorylated proteins and phospholipids in immune system cells. And among which you find ERK, which is actually something that is generally studied for cancer therapy. And then you have the second graph that represents that the relationship between different risk factors, but also different drugs, and PSA, which is process-specific antigen. And in general, I'm going to use this notation in which gray variables are intervenable variables, red variables are, the red node represents target variable, and targets, I will define why it's called target in a second, and brown nodes are non-intervenable variables. So these are variables that we can observe, they are not hidden, but we cannot manipulate, we cannot intervene. So I cannot go and change your age, for example, or I cannot go and change the BMI directly, I'll have to do something to induce a change. Okay, so you can ask me a question about the other algorithms, but today I'll focus on causal Bayesian optimization because there's been a few developments in the past few months, and so I'll try to give you a bit of an overview of what the literature that exists. And I'm going to be focusing a lot on how to integrate observational and interventional data, which fits perfectly with how we ended the previous talk. Okay, so in general, in a lot of different disciplines, social science, healthcare, biology, operation research, what we want to do is we want to solve an optimization problem, which is a global optimization problem. So in a global optimization problem, we consider the existence of a graph, like the causal Bayesian network that you've seen before, that has some nodes V. We have a target variable y among these nodes, for example, PSA or ERK that you've seen just now. And then we have a set of variables that is generally a subset of all nodes in the graph, which are intervenable. So I can go and actually do interventions on them. Interventions are costly, so I have to account for cost every time that I intervene, which could be any sort of metric that is probably going to be application specific. And every time that I intervene on a variable. So I intervene, for example, on X, which is a subset of all is a set in the power set of the intervenable variables, according to some intervention domain. So let's say I can intervene and change the temperature of the room, but I can do it between 5 and 10 degrees, or 5 and 20. So I have some range that I can intervene. And while bandits focus on discrete values of intervention, so intervene or not intervene, generally, here I'm going to talk about continuous variables, so temperature. Should I set it to 25 or 25.5 or 26 and so on and so forth. So what we want to do in a causal global optimization is we want to find the optimal intervention set, capital X star, and the optimal intervention level, this is the small x star, that are minimizing, but it could also be maximizing, the target effect. So this target effect, which I'm going to use is mu, this is the expectation of y under the interventional distribution. So this is the distribution that we were looking at before, P of 2, and this is just the expectation of this variable with respect to this interventional distribution. You might see it written also has the expectation of y given 2 of x. And so the search space of this algorithm is a bit different from what we are used to, because we want to look at both the set x, which is in the power set of intervenable variables, but we also want to look at the domain. We also want to identify, the intervention level x in the domain of all the possible intervention values. Okay, so one way to solve optimization problem in machine learning is Bayesian optimization. So in Bayesian optimization, you generally use Bayesian optimization in setting where you want to optimize a function. You don't know the explicit form of this function. So you want to use models, probabilistic models, to put a prior on this function and then sequentially get sort of evaluation of this function to find out the minimum or the maximum. So when the target function is unknown, multimodal, expensive to evaluate, perturbed by noise, which are all characteristic of the target effect, you might want to use Bayesian optimization. Now, when this is all true, so the function is unknown, multimodal, perturbed by noise, costly, and you also have a causal graph that describes the relationship between inputs and outputs, so there's a structure in the problem that can be represented by a causal Bayesian network, then you might want to use causal Bayesian optimization. So I'm not sure how many of you are comfortable with Bayesian optimization, so while talking about this, I'm just going to try and make a parallelism between the two. Okay, so let's make an example now. So for example, let's go back to the healthcare setting where we want to minimize the probability of getting this cancer, so the probability of PSA. We have a variable, the target variable is PSA. We can intervene on what? We can either intervene on statin, or we can intervene on aspirin, or we can intervene on calories intake. These are the 3 things that we can do. These are the gray notes. But we can also think about in combination of interventions. So for example, I might want to combine statin and aspirin, or statin and some diet that is going to decrease the calories intake, or I might want to intervene on all of them. So I need to consider all possible combination of intervention that I can do in this system, and this is written as the power set that you see P of I here. So I do my optimization, I run causal Bayesian optimization, and what I get is that I should intervene on both the 3 variables and set them to this value. So this is going to be typically the output of this algorithm. What is the problem with this, though, is that the space to explore is quite complex. So we need to sort of try to restrict the search space in a principled way. We need to model the target effect, considering that we have available 2 types of data, observational and interventional. And we also need to define an acquisition function that allows us to sequentially explore the space of possible interventions. So an acquisition function is just a function that tells you, okay, next you should collect this intervention on calories intake and at level 1. Then I go, I do the intervention, and the acquisition function will tell me, well, then next you should collect instead this intervention on statin at level 1. So how do we restrict the search space? I'm going to go a bit more in detail in causal Bayesian optimization first, because all the extensions are going to use the same principle. So you're just going to see modification of these 3 elements that are how to reduce the search space, how to come up with a probabilistic model that accounts for the uncertainty and the complexity of this target effect, and how to explore the space with this acquisition function. That's all. There's actually another point, which is the 4 that I put here, but I'm not going to go in the details of that because it's not common to all the algorithms that we're going to speak about. Okay, so first thing is how to restrict the search space. Well, we want to do that, so we want to get rid of some of the possible intervention that we can do by ensuring that the solution of the optimization problem is kept within the search space. So I want to say, okay, maybe I don't need to intervene on statin, aspirin, and calories intake because there's another intervention that is less costly and that will allow me to get to the same output. So if by intervening on statin and aspirin I can get to the same output as intervening on calories, aspirin, and calories intake, then I prefer it. So there is an implicit assumption here, which has been used also in causal bandits, that intervention on sets of smaller cardinality are better. You can think about it as an intervention cost, but there is also other probably, assumption that you can make justifying this. So in general, you can reason, looking at the graph, you can actually think about the do calculus rules that I spoke about before. And you can see that, for example, in this graph x, z, and y, x is independent of y given z. Stop. Come back. Right. So because this is the case, so y is independent on x given z, what we have is that the expectation of y under an intervention on both x and z is equal to the expectation of y under an intervention only on z. So if I do an intervention on x and z at the same time, I get the same output that I would get by just doing an intervention on z. So why should I do an intervention on both variables? That is probably more costly. So doing this type of reasoning for all the sets in the power sets, you get to a smaller search space. Okay, so for example, in this case, it's quite a simple problem. So in this case, we can get rid of the intervention on x and z and just focus on either intervention on z or on x or on the empty set, which means no intervention. Okay, now that we have restricted the search space, so we took care of the part that is circled in red there, we need to take care of the second part, which is how do we model the target effect. Now, because we are dealing with continuous variables, this target effect is actually a function that gives you the expected value of y for every possible intervention level x. So what we can do is, as in standard Bayesian optimization, and to keep the tractability of the problem, put a GP on this function, so a Gaussian process. So a Gaussian process on this function that is g of yx with a specific mean and a kernel, m of yx and s of yx. Now, you can just use a Gaussian process and not specifying anything from them, so just use a zero mean function and an RBF kernel. There's nothing that prevents you from doing that. But this would sort of slow down your identification of the speed at which you're able to identify the optimal, because you're disregarding some information that you have about the system that comes almost for free, which are observational data. So observational data are generally cheaper. They are available in larger quantity. And if causal effects are identifiable in the causal graph, they can be used to get an approximation of your target effect, which is what you want to model. So what you can do is you can get your observational data and compute an estimate mu hat of your target function using the rules of the calculus. Then you will have a problem of how you estimate it. You can do it in different ways. We just use a plug-in estimator. We don't do anything fancy for that. But you're still going to provide, even with a very basic estimator of the identification formula, you're still going to provide some information about how the target effect, how you believe that the target effect should be in the interventional domain. Now, because observational data are noisy, we also have some uncertainty to take into account. So we provide this mean function, this estimate target effect, but we also want to inflate the variance that we have around that function to account for our uncertainty and the computation, the uncertainty that we have also due to the estimation problems of the identification formula. So we can do that by saying, okay, I'm going to get an RBF kernel, that is the first part of the kernel that provides me some flexibility in how I model the target effect, but I'm also going to add this term, this product that is a linear kernel, that gives me some uncertainty about the mean function that I've set. Okay, so this is quite an important point. So we'll try to explain it with a plot. So suppose again we are in this setting in which you have x, z, and y, and we've seen that we want to intervene on x, and we want to intervene on z, and we want to also account for the possibility of not intervening. Now, for each of these sets, I have a model, which is my target effect. So I will have my target effect under an intervention on z, my target effect under an intervention on x, and here I'm plotting the target effect under an intervention on z for a specific linear, no, it's not linear, for a specific structure, for a specific joint distribution associated to this causal Bayesian network. Now, the black line gives you the ground truth function. So this is the true target effect that you want to find out, of which you want to find out the minimum, while the red line and blue lines are giving you the prior mean and the posterior mean of the Gaussian process model that you put on your target function. So the difference between these two plots is that in the first plot, I'm using a standard zero mean RBF kernel. In the second plot, I'm using a mean function and an RBF kernel plus one term that are estimated with the observational data. So this is a way to combine observational data and interventional data. So what you get is, you see that in the first case, you have a prior mean that is a 0. You collect interventional data, which are the red dots, that are we just have like 3 in this case, just a few. And you get a posterior mean with an uncertainty that is given by the shaded blue area that passes through the points that we collected, as you would expect in a standard GP regression. And you see that, for example, you don't, actually I should say that the domain, so this x-axis, is the domain that we saw d of x that I'm allowed to set the values of z to. So the problem here with the first plot is that between -2 and 0, I don't know how the function behaves. So according to my model there, I would estimate that the minimum is a 0, and I would go ahead with an intervention of z at type level 0. However, what happens when you use observational data in the mean function is that you get a good representation of your underlying function even in areas where you don't have interventional data. So in a way, you're augmenting your data set with data that are noisy. So you can think about it as a sort of multi-fidelity model if you're familiar with that. So what happens is that you see in green all of these crosses that are on the bottom of the plot that are in between -2 and 2, because naturally when I observe the system, I observe z values that are between -2 and 2. And then you compute you can see that basically the mean function, both the prior and the posterior, are capturing this drop of the function in between -2 and 0, because that's where I observe observational data. And so by just collecting 3 points, I have identified basically what the minimum is. And I can do an intervention on z at -1.5. Now, obviously, this idea works in setting where you have an interventional domain that covers the observational domain. So if you want to intervene on -4, if your minimum is at -4 and you don't have observational data for -4, this prior formulation is not going to give you more information. So you will have to go and actually intervene on that point to find out how the function looks like. Okay, question up to here. Yeah.
So one of the things that is the effect the hyperparameters have.
Yeah.
So I guess obviously that also happens.
Yeah. You inherit all the problems of GPs and Bayes opt. So in this case, actually, it depends a lot on the observational data, how much observational data you have as well. But yeah, you have exactly the same problem. Here we didn't do anything specific, we just used a RBF kernel with 1.1 as initialization. It turned out fine, but it's very application specific as well. And obviously you could use any other kernel here, not specific, not necessarily has to be an RBF. It's just the idea of a combination of a kernel that gives you some flexibility and one that reflects your uncertainty about the process. Okay, so once we have these models, so we have our GP models, then you proceed as you would do in a standard Bayesian optimization. You get an acquisition function, which is in this case an expected improvement with respect to the posterior GP GYX on your target effect. And then you compute this quantity here, which gives you the probability, basically the expected value, the probability of observing a value that is better than the one that you have observed so far. Better in the sense that you're trying to minimize, the minimizes more, let's say. Now, the only different things with respect to Bayesian optimization here is that, first of all, you have this Y star. So in Bayesian optimization, you have one function, you have one model, you have one acquisition function. Here you have different models, and therefore different acquisition functions. So different function, which are the different target effect for different set, different model, different acquisition function. So when you compute the expected improvement, you have to compute it with respect to the optimum that you have observed across all models. So this Y star is computed across all the target effect. Let's say I have observed an intervention on Z, and I've collected the Y value of -1, then I collect an intervention next, I observe -2, what is the optimum between these two, -2, and then this is going to be the value that I use to compute the expected improvement. There's another factor here, which is the cost, and this is, so it's a unit of improvement per intervention cost, and so the cost can be anything that you want. So it is, I wrote here as a cost that might depend on the set that you intervene on and the value, but you can also have, for example, the intervention cost that depends only on the number of variables that you intervene on, the cardinality of the set X. And so what happens is that you compute an acquisition function for the first function, an acquisition function for the second function, you look at the maximum of these two, these are the red and black dots, you compare the two, and you decide which one to intervene on. So you do this recursively, so you have a number of trials, you start with your prior models, you collect interventional data, guided by this acquisition function, and then you get to hopefully to the optimum. So I'm going to use an experimental result here, so synthetic result here, just because it shows case a bit more what happens, and then we'll see some example in healthcare and biology. So here, what happens, so I'm trying to manage, so I've looked at an example that is slightly more complicated than the XZY. So we have a graph that you see on the left, where we're trying to minimize Y, we can intervene on B, D, and E, we can observe A and C. We have these bidirected edges, which are hidden confounders. There's something there that affects A and Y, I don't know, I cannot observe it, I just have to take that into account. And so we run BaseOpt, so standard BaseOpt. So what does BaseOpt? So BaseOpt intervenes because it doesn't account for the existing causal relationship. It intervenes on all the variables at the same time. So in general, in BaseOpt, you want to minimize a function, maximize a function. What you do, you take your input and you just change all of your inputs. So BaseOpt will intervene on all the variables that are manipulative in the system. And then we can run instead CBO. Just, these red and dash are just different search spaces, but it's not relevant for now. And you can see the first thing to notice is that BaseOpt converges to a completely different solution, which is the orange line. So these blue lines are BaseOpt, and it converges to the orange line. And why it converges to the orange line, which is a completely different optimum, is because it breaks all the existing causal relationship in the system. So by intervening on B, D, and E, for example, it blocks the way in which B can reach Y. Okay, but you might actually want to exploit that. It might be that not leaving some of the edges in the graph helps you to get to a target effect which is better than the one that you would get by intervening on everything. So it solves a completely different, basically, optimization problem. So you do really want to, not only account for the cost, integrate observational and interventional data, because it allows you to converge faster, but you also want to think carefully about what the graph is telling you about the search space. So base-opt converges to the orange line, and then CBO converges to something better because it only intervenes on B and E. So because of the dependencies, the causal dependency that you have in this graph, it forces D to take some values that you wouldn't be able to set with base-opt. Questions? Yes. Yeah, but the problem is, how do you run random search? Do you run it by exploring the same search space of CBO or the search space of base-opt? Yeah. So there are these lines in the paper. I haven't shown them here, but we've done exactly the same. It just performs really badly compared to this. I think in one of the other methods I have the random performance as well. But this is synthetic, right? So we'll have to try with healthcare as well. When you speak about restrictions, you mean like that you want to ensure that when you intervene on B, D doesn't take some values, or? Mm-hmm. Yeah, so that is automatically accounted for by the fact that I'm intervening in a system that has its own distributions that I'm not touching. So when I'm intervening on B, I'm not touching the distribution of C given B or D given C. These are just unchanged from the original system. However, in some cases, and we're going to talk about it, you might want to restrict the type of value, especially like if variables have like a specific meaning, like risk factors in healthcare. You do want to have a bit of more control on the system, and we're going to speak about it in 10 minutes. Okay, so there are a lot of limitations of this. This was the original work in causal Bayesian optimization. So there are a lot of limitations that people have addressed in different ways. For example, the fact that you might say, oh, we have a graph that is very big, we have a large number of models, how do we deal with that? How do we transfer information across environments, across to hospitals, for example? How do we transfer information? Let's say I've intervened on X. What does this tell me about an intervention on X and Z? There must be some information there. I'm not taking that into account so far because I'm just using dependent models. There are other two issues that are particularly important, I think, in healthcare, which are, here I'm dealing with hard interventions, which might not be what I want to do, because I might want to take into account other variables to be able, for example, to set statin as a function of age and BMI. And also there might be constrained variables. So there might be variables that I don't want, so I don't want to intervene, or I cannot intervene, but I want to keep them within a certain level, let's say. And there also then there is the case that there is the possibility of having an unknown or partially unknown graph. So that's what I would like to get. Let's see if we get that. Okay, so all of these alternative scenarios can be handled within the same sort of framework of having an optimization problem, having a search space reduction, a model that characterizes your target effect, and an acquisition function. So I'm going to follow the same sort of method. So for example, something that we just mentioned now is the existence of constrained variables. So let's say you're in the healthcare setting and you're trying to minimize PSA, but you want to do that by not pushing BMI to get to a value that is going to be unhealthy for a patient. So I don't want to be able to minimize PSA by making a patient obese. So what I want to do is I want to constrain that variable to be within the healthy level. So we just put a constraint to 25. So the pink value, the pink nodes now are protected or constrained variables. And notice that we could have protected variables that can be intervened or protected variables that cannot be intervened, and a combination of these. So again, we have the same setting, just a different set of variables that allows us to define a slightly different optimization problem. So it's exactly as before, but we also want to ensure that for a set of variables, the constraint effect, which are again just the expected value of an intervention on a variable C, is kept below or above a certain level. So something to notice is that if variables are at the same time protected and intervene, how do I make sure that the constraint effects, so that the constraints are satisfied? Well, just making sure that the intervention values that I consider, d of x, are within the threshold that I'm setting. So I cannot, let's say, ask for, well, BMI is non-intervenable, but suppose that it was intervenable, I cannot ask for BMI to be kept within below than 25 and then intervene between 26 and 27. So that's sort of like, we assume that the threshold values are set in a way that are consistent with the intervention values. Okay, so let's take a step back and rethink about a bit what we are doing with non-causal optimization, causal optimization, and constraint causal. We have exactly the same characteristic in terms of the function that we're trying to model, because the function is unknown, it's perturbed by noise, is expensive to evaluate, has a cost. And so we basically incorporate additional elements in this optimization problem. First it was the causal graph, now is the causal graph and constraint, and we modified the Bayesian optimization to reflect this. That's all we're doing. Again, constraint in this case needs to be unknown, because if it was known, then it would be sort of could restrain the search space to start with without having to incorporate that in the optimization. Same framework as before. Again, you can restrict the search space, you can model the target effect, and then you can define an acquisition function. The constraining the search space is way more complicated in this case, because it requires some additional causality notions and do calculus manipulation, so we'll not look into that. But we can look at how to combine interventional and observational data to come up with a better target effect model. So now, something to notice here is that in general, in BaseOpt, people have thought about multi-objective optimization, and so they have come up with models that account for the correlation existing among different objectives, but they haven't considered the existence of correlation between constraint and target effect. However, in causality, there is a correlation between the target and the constraint, which is induced by the graph. So we don't want to use independent Gaussian GPs to model the target effect and the constraint effect, because this would require to collect even more interventional data to update our belief about the constraint and to be able to identify the optimum. So we want to exploit as much as possible these two sources of data. And we do that by keeping the same computational tractability of standard BaseOpt, so still with GPs, but modifying this mean function and kernel function to reflect that. Okay, so we speak about single-task Gaussian process model or multitask Gaussian process model. Now, in case you don't believe that these functions are correlated, we can look at one case together. And to do that, I try to avoid it, but we need to introduce structural causal models. So structural causal models are just, associated to one of the graphs that we've seen before. So you have a Bayesian network, causal Bayesian network that is associated to a structural causal model, which is a tuple that includes what? Some variables that are U, exogenous variables, some variables V that are the nodes in the graph, some function F, and the U, they have an associated distribution P of U. And so these functions are a set of deterministic functions that are known, okay, that are associated to each variable. So this is just a way to formalize with these functions the sort of like the dependency between variables in this causal Bayesian network. So for example, in this graph X, Z, and Y, we can think about, x being alpha u of x, where u of x is a Gaussian, z being a linear function of x plus some random term, and then y the same, beta z plus some random term u of y. And here I'm assuming that all of these exogenous variables or unobserved variables, they have a standard Gaussian distribution. So here I'm just assuming that these functions are linear. Actually, they're unknown, so we'll have to learn them. But in this setting, so if everything was linear and you were doing an intervention on x, then you can see that the target, there is a target effect, and for x there is a constraint on z, which is mu of z, and you can show that the expected value of y under the intervention is just beta and the expected value of z. So obviously the correlation is not going to be as simple in nonlinear model, but there is some sort of information that we can share by modeling the correlation between these functions. Okay, so there are different ways that you can model this correlation and different models that you can come up with. And so I'm going to try and describe a bit what they are at a very high level, because it's going to use some notation of multitask models. So the first simplest case is to just disregard the correlation, okay? So we do as before, we model every target effect and every constraint with a standard GP that has a zero mean and an RBF kernel, and we proceed as before. This is the box on the left, which is exactly what we were doing before. Still using observational data. So you can even just completely disregard observational data. So we'll see we look at the performance of all these alternatives, but STGP stands for single task Gaussian process, and when you see the plus, it means that it uses the observational data. Otherwise, what we can do is a multitask model, which is an intrinsic regionalization model for those that are familiar. And what we do is we assume that there are a set of latent functions, there are Q latent functions, and the linear combination of this latent function gives you all of this target and constraint effect. And then what we do is we again incorporate the observational data in the mean function. So the correlation function, the correlation structure is reflecting this idea of having this underlying linear combination of GPs, while the mean function is still going to be computed with the observational data. So you have a multitask GP that uses zero mean and correlation structure of the SEM model, and you have a multitask GP plus that instead uses the observational data in the mean. However, we are not again fully exploring what we know about the system with this, because what we do here when we use this latent function, we say, well, we don't know, we just initialize this latent function to the GP, standard GP, and then we try to learn the parameters of this linear combination just with optimization or whatever method you prefer. But we do have some knowledge about the correlation structure. As we saw before, we knew that the expected value of y was the beta times the expected value of z. How can we reason about that? Well, what we can do is we can take a model-based approach, and we can say, okay, we have a structural causal model, and that's why I've introduced structural causal model, because in this case, we really need to think about the functions that are behind this system. And we say, okay, every variable v is a function of its parents plus some random term. And notice here that only now I'm making the assumption of no hidden confounders, because I do need to model explicitly my structural causal model, and otherwise I would go into latent variable models. I might be able to do it anyway, but we haven't tried it. So I'm assuming that there are no hidden confounders, so these dashed edges don't exist anymore. I'm modeling the function of the structural causal model, and I'm again with GPs, but again, you can do whatever you want here. And then what I do is I've learned I can fit this function of the structural causal model with observational data, so I'm reusing this observational data in a different way. And what I do is I sample from the structural causal model. So I get the posterior of this function and sample values of this v to compute an empirical estimate of what the mean should be and what the correlation function is. And I know this is complex, so we can make an example. If we go back to this case here, this is linear, but let's assume that gamma x is just a function for z. What we do is we fit gamma, we fit beta, and what we do is we sample, and I'm assuming a Gaussian distribution for this variable, for this u. So I sample a value of x, I compute the gamma estimated x, so I sample a value of z, then I sample a value of y, and I do that repeatedly. And so what I get is some sample of y, some sample from the learned structure of causal model that I can use to compute the correlation, empirical correlation between different functions, and also the empirical mean. And in this way, it's a different way of using observational data that also accounts for the function, right? Because you have a composition of function, in this case, that is driven by the graph. Questions? So these results are in the healthcare example that we've seen so far, where we try to minimize PSA by intervening on statin, aspirin, and calories intake. And there you see random here, and in the method, you see all of these methods that I talked about. So the last one is this GMTGP, which stands for Graph Multitask Gaussian Process. And you see that, first of all, obviously, CBO is included there for comparison. This is the method that we saw before, but it solves an unconstrained optimization problem. So it converges to a completely different optimum, which is the dotted line. So the constrained optimum is the solution is the 5.2 level. This is the bar there, the red solid line. And you see that what happens is that, well, this is a way more complicated example than the synthetic. You can go and see the synthetic, but it happens that the model that are MTGP and STGP, they do exploit observational data, but this is not enough to reach convergence. A model that incorporates observational data, interventional data, and the graph structure, which is the black line, converges and so identifies the optimum intervention in something like 5 trials, which is the convergence there. This is not the only thing that we care about, because we also want to understand how we got to these results. So we converge, but how many interventions did I do that were not feasible? Okay, so there's no guarantee here, unless you switch to a safe Bayesian optimization framework, that you're not going to collect interventions that are going to hurt patients. So this is not applicable, so at this stage, at least, in healthcare. It has to be extended a bit more. But in this case, you show that because you've accounted for these correlations, so you properly account for uncertainty that you have around your function, you also collect 100% of feasible interventions. So we're looking for a trade-off here. We're not only looking for fast identification of the optimal thing that we want to do, but also we care about how we get there. If we get there with a higher number of experiments, but collecting a majority of feasible intervention, that's way better. And you can do the same for the biology example. This is the genomics example that I was speaking about before. For the immune system cells, where we try to minimize ERK by not affecting pKa and pKc, because these are generally considered important for the healthy functioning of a cell. And so in this case, constrained and unconstrained optima are the same. These are the red solid line. And you can see that indeed, in this case, the single task GP and the CBO actually converge pretty fast. They don't have the complexity of these other models that require estimating the function and computing these empirical measures. But at the same time, the problem is that they collect a very high number of no feasible interventions. So using a slightly higher number of experiments has the blue line and black line, but collecting the majority of feasible intervention is probably more appropriate in this setting. Yeah. Yeah, yeah, yeah. Indeed. Yeah. It could be a big problem because if you think that there are variables that create confounding, that you should include them. So in this case, if there is something else has, I don't know, compliance that affects the way in which you take aspirin or statin, you should include that variable there. Unless it doesn't have, unless, for example, it only affects statin and it doesn't affect any other variable in the graph. And in that case, it can be absorbed in this sort of random noise that you have because it doesn't create confounding. So in general, you're sort of like saying, this is the graph, there is nothing else that should be accounted for. Yeah. Indeed, this is what, for example, in this case, it's clear that if you look at AKT, and AKT is not related to RT, when you go through the procedure of the search space, which I haven't discussed, you'll get rid of AKT. Like, intervening on AKT is not going to affect what you care about, so you just shouldn't do it. But, you know, something like this, now this is a very simple case, but we tried it with graphs that are way bigger, like in ETH cells, in which there are around 250 different nodes, and by doing this search space, you can go from something that wouldn't be manageable to collect in a wet lab to something like 30, 40 interventions. Okay. Okay, so this is the most interesting part, I think, but let's see. It's also the most difficult to explain. So up to now, we looked at hard interventions, in which you fix the value of a variable to a constant irrespective of anything else in the graph. But if you look at this graph in the healthcare, you can think that statin and aspirin are actually, these edges between age and BMI are the result of a previous policy that was implemented by a doctor as an existing policy. It's not something that comes out in the natural world. So in general, what you would want to do is you would want to find the intervention that for statin and aspirin or calories intake that account for some other variables in the graph. So instead of using P of x given the parents of x, which is the distribution in this causal Bayesian network, you want to use an alternative distribution, which we call this pi x given cx. Okay, so you want to substitute a distribution in the graph with an alternative one. So this is what people have called soft interventions, or other people in BaseOp they call contextual, or also using contextual bandits. So for example, as I was saying, instead of fixing the value of statin, you want to replace phi of statin given age and BMI with pi of statin given age and BMI, and take these two variables into account. Why do you want to do that? Well, for targeted and more personalized treatment, for lower cost, because you want to give the treatment to people that are actually going to benefit with it, and also for subgroup optimality. So while you do something, you intervene on a variable, you don't want to make sure that you're not hurting other subgroup of the population. You want to benefit everyone. And also because hard intervention are just a special case of this type of intervention in which this distribution pi x cx is just a delta function. And so there's no loss by expanding this search space to consider soft or contextual intervention. So this is a problem that has been analyzed just this year, in the past 2 years maybe, by these two papers that I've added references here for. And the first one is called Contextual Causal BaseOpt, which is Cockaboo. And the idea here is that they use exactly the same example, and they say, well, actually, what you should do is you should solve an optimization problem with hard intervention, but for conditional target effect. So instead of having expectation y given do of aspirin and statin, they say you should condition on age and BMI, and for every value of age and BMI, you should find the right RD intervention. The shortcoming of this approach is that to do that, you need, so they use a model on the contextual variable, the intervene variable, and the target, and you need to have access to the context before deciding which intervention to give. So you're a doctor, you have a patient, the patient tells you, these are my contexts, and then you decide which treatment to assign. So you don't have a policy in a way, you have a discretized version of the policy. And the problem is, suppose that you want to deploy your policy in the system and you don't get to see the patient, you just want to set up a rule according to which the patient go and get the intervention that is good for him or her. And it also has some technical issue on the modeling, but let's not get into that. Another way that people have thought about this is to use a model-based approach, again, in which we completely get rid of the modeling of the target effect. We model explicitly the structural causal function as we did before, and we use this action variable there that are what you're allowed to change to be able to induce a change in the distribution of this variable. So you have action variables, you can set them to 0, 1, they're actually continuous variable, and that is going to generate a change in the distribution of one variable and therefore of all the variable downstream. And the only problem with that is that, as we were doing before, here you cannot account for hidden confounders. And generally, modeling the structural causal function is quite difficult. Now, another way, it's just another way to think about this problem, is to frame it as we did so far. To frame it as an optimization problem, in which instead of now considering a search space of intervention values and intervention variables, we think about mixed policy scope. So mixed policy scope is just a collection of intervention variable context pair. So for example, let's look at an example. I'm just going to go on. Okay, so in this causal graph here, you can think about a mixed policy scope has this thing, the S that you see here, that tells you that you intervene on statin, accounting for age and BMI. You intervene on aspirin, accounting for age and BMI. You intervene on calories intake, accounting for nothing. This is a hard intervention. You can have another mixed policy scope that tells you you intervene on statin with no context, so hard intervention, and you intervene on aspirin with age and BMI, and any possible combination of hard and contextual intervention. The search space explodes, so we'll have to do something exploiting the graph to be able, again, to reduce the space. So this is the search space. Instead of having intervention set, you have mixed policy scopes. And then what is the value in this case? Well, the value is a collection of functions. Okay, so instead of having a value, let's say calories intake 1 or statin 1, what you have now is a function, pi, small pi, statin given age and BMI, that tells you for every value of statin and BMI, sorry, the age and BMI, what values of statin you should assign. And you can do then also the hard intervention case as we were doing before. Now, there are various challenges with this problem, and people are still thinking about in which cases this type of intervention are useful for this causal decision making. There's also a problem because here we are looking at a functional optimization problem. So the argument of what we want to find are functions. And we look at mixes, right? Mixes of hard and functional. And then we need to find setting where this actually has a benefit, because it does complicate the optimization a lot. So in general, for the conceptual part, it can be shown that two things. Looking at deterministic intervention, which simplifies the problem, is optimal. So you're good, so you can look on deterministic functions. And you can also show that you should look at functional contextual intervention when there is a parent of y in the graph that is non-intervenable. So if a parent of y is non-intervenable, is not in I, or there is an hidden confounder on y, then you should do that in general. Now, in terms of modeling, what happens now is that your pi, so this Gaussian process model, is a function of a function. Pi is a function, is a collection of functions for every intervened variable. And so what you want to do is you want to do what you did before. You want to have a mean function and kernel function that sort of incorporates this knowledge of the system that you have. Yeah. But you observe the intermediate input, the intermediate output. So that's the difference. You observe the intermediate outputs, but yes, it's a composition of GPs. The problem here is that this kernel has as input to pi and pi prime. These are vector of functions. Okay, so it's a vector value function defined on input space of different dimensionality. So I think I don't have an example, but think about, maybe I can go here. You can have a function on W that depends on Z, and you can have a function on Z that depends on X and W. And you need to model these two as inputs of a GP. So what we came up with was to think, okay, what we need to do to compute this GP is to actually come up with a way to compute distances between functions. And the way you do it is, one way, is to assume that these functions are in an RKHS, it has a kernel that allows you to compute this distance here, has a dot product. So we say the function that we consider our function in our RKHS, which is this one, HKS, with the reproducing kernel kappa, that allows you to compute this distance. There is a bit more complexity of how you actually write this kernel because of this different dimensionality, but the important thing is that you can do it in a way. So you can hide all of your complexity of the function within this parameter of the GP and just keep the tractability of the problem. Yeah. Kind of, yeah. There are thousands of possible things that you can do here to come up with kernels that are more structured. Because the problem is now, for example, you can think about these pies, the different pies, let's say a function on statin and a function of aspirins as basically these tasks. You can think about these are two tasks that are defined on different input spaces. So you can think about, okay, I'm just going to assume that their correlation is 0. But what if I want to make sure that I account for this correlation? But they're defined on different input spaces. How do I do that? I need to reflect, maybe there is a proposal to actually consider the overlapping part of the input space and reflect that in the kernel and then disregard whatever is the input space that differ between the two. There are different ways. The important thing is that basically once you have assumed that these functions are in an RKHS, then you can come up with different kernel structure as long as they're kernels. So that's a bit of the experiments that we did. Maybe, no, I think we have to go through this because it's important to see that now what we are doing here is we are learning that the optimal thing to do for static is this red line. It's not a value of 1, it's not a value of -1, it's not a value of 0, it's a function. So what we do is we start looking at the space of function and we do numerical optimization. So another big problem is how do we actually explore this big space that is an RKHS. And so what happens is that you can basically still converge to a value. So you have again, redefine an optimization problem that does not necessarily have the same solution. So FCBO, which is functional causal Bayesian optimization, converges to this solid line red. The others are only either considering an intervention on all variables simultaneously or wholly Hardy intervention, so they converge to suboptimal values. And the important thing again is this function here. So CBO would select, okay, Z and W at level -1, 1. FCBO would say, okay, the optimal thing is an Hardy intervention on W, but for Z you should account for X. Okay? And so for healthcare, this is very important because if you look at the gain that you get from implementing this policy, which is the difference between what you would get in your output by not doing anything and doing the intervention, you see that FCBO achieve a gain for these two populations that are subpopulation X lower than 0 and X greater than 0 that are approximately the same, while CBO is forced to just set an intervention that is the same for everyone, and so it might work well for a subpart of the population, but it might not work well for another part of the population, has X greater than 0. And the same happens for healthcare. So it's way more expensive, so it takes way more trials, FCBO, to converge. But these are the type of function that it learns. So FCBO learns a function that is very structured on the age BMI sort of space, while CBO is just a hard intervention, so it's flat for everyone. I don't think we have time, but exactly the same type of reason can be followed to account for uncertainty in the graph. So suppose that you have in your healthcare, you know part of the graph, you don't know how BMI affects PSA, or you don't know these red edges. Then once again, these are unoriented, you can modify your target, your model and your acquisition function to account for uncertainty in the graph. So the easiest way to do is to, well, rephrase the optimization problem and to say, I'm going to place a prior on my graph. I'm going to update my prior as I collect observational and interventional data. And then I'm going to use my current belief of the graph to compute the target effect, to compute my mean function and kernel function on the target effect. Exactly as we were doing before. The acquisition function is way more complicated because it's an entropy-based acquisition function, but you can still sort of do that in the same framework, in the same line of reasoning of search space, target effect, model, and acquisition function. And we can skip. And I'll conclude by saying that what we've seen is that we can exploit the tools of statistical causality to solve various decision-making problems, which might emerge in different disciplines and also in healthcare and biology. And we can use a sequential strategy to explore different interventions via an acquisition function that accounts for constraint, known graph, different type of interventions, and especially reducing the search space by exploiting the graph. GPs are a way to keep the tractability of these problems by also accounting for different sources of information, so observational data, interventional data, and the structural causal model. Therefore, quantifying uncertainty, that's the key, in a better way, and thus making the decision-making process more efficient. Thank you.
Thank you. Thank you, Virginia. Are there any questions?
Thank you very much for a great talk. A question just related to kind of the final slide, actually, in creating these graphs. I assume that usually it's based on observational data and experts in creating these graphs, but when you've got these very large graphs that are just crazy unknown, like the cells with hundreds of nodes, could you use graph neural networks in some way with edge attention, maybe node classification, to try to actually decide what these graphs are?
Yes, you could. The problem with that is that using GPs, you can sort of keep the tractability of a closed form posterior update, so you have to try and find a way to do that, but yes, you can definitely do that.
Thank you.
Any more questions?
Yeah, just a quick one. So is there a way to basically combine this hard intervention with the functional so that you can kind of save a bit on time on things that you don't, like the complexity? If you can kind of make it less complex by maybe making such a soft intervention on some things while hard intervention on others, because...
This is exactly what this does.
Yeah.
So, for example, the solution here, S star, tells you that you have a hard intervention on calories intake, and then you have a functional intervention on statin, because it has a context that is not empty, and then you have a hard intervention on aspirin. Something interesting that has not been done is if you want to make the mixed policy scope S be dependent on another variable. Suppose that you want to use, let's say you want a function defined by parts. Okay, so you might want to have x equals x lower than 0 hard intervention, and then x greater than 0 functional intervention. That's something that we haven't considered, but you might be able to do it.
Okay, yeah. That's kind of what I meant, yeah. Thank you.
More questions? So I have a question. What is the most complex causal graph you have used this algorithm?
So we've used it for this cell that had around 200 nodes, 250 nodes. The only reason why we were able to do it is because there was a very, very convenient structure for which we were able to reduce the search space a lot. And because, you know, scalability and the fact that we still need a lot of GP models to handle it's an issue. So in that case, yeah, we were able to apply it, but I wouldn't say that it's a method that is scalable to very big graphs. And obviously, with this additional, this functional extension, the exploration of the RKHS where these functions lie, it's a big issue as well. So numerical optimization is a way of doing it, but you know, exploring closed form gradients, functional gradients could be a direction. It's not very efficient at the moment.
Any more questions?
Just one question about the distribution of the target. Would that have an impact? All right. Is the methodology like applicable for different target distribution? For example, if you are interested on for example, I see like the GP is the main thing in the thing. So if I'm working on a target distribution where GP is not applicable.
So if you're dealing with a discrete distribution, I would say that your problem looks more as a bandit problem. So bandits generally deal with variables that are not only the target, but also the intervened variables are discrete. If you're thinking about, and that's a problem that we are thinking about as well, if you think about, I don't know, data that are from a Poisson or any other sort of distribution, that's not being done.
Okay, so I think we can wrap up here. Thank you, Virginia. And we have lunch now. Thank you.